Okay. Hello, everyone. So it's indeed a very great pleasure for me to be here and to talk today about carrier transport and I will focus mostly on bulk, but I will also touch a bit on 2D materials. So the plan for today is to start with the description of different types of charge transport. I will briefly go through them and I will focus on one of them. And then the idea is to start from Feliciano's many-bodies lecture and to show how you can get from a fully many-body description of transport and make a series of approximation to get to the Boltzmann transport equation that we will use this afternoon to compute mobility in semiconductor and metals. So this first part is quite involved mathematically, but I really want to sort of show that it's really possible without hiding any steps to go from that many-body framework to the Boltzmann transport equation. But then it will become sort of a bit more relaxed. So then I'll present some semiconductor result. I will talk about the whole mobility. So this is when you apply a magnetic field. I will touch a bit on the carrier impurity transport that you will also have a session on given by Dr. Vietran Ha. And then I will present some result on metals and a brief outlook. Okay, so when you have electron or holes, so basically charged particles, they can move as a result of different force. It can be a density gradient, so this is simply diffusion, or it can be due to a temperature gradient, so this is thermoelectricity, and you have things like the phonon drag contribution. But also, you can have the movement of charge if you apply an electrical, an external electric field, and this is called drift mobility. And in that case, basically what happens is that you apply an external electric field and the charge, the electron or the holes, they will start to move as a result of that applied field. And the movement of this charge will be impeded, reduced by different scattering mechanisms. So there will be an intrinsic one, which is simply the scattering with the lattice in which they propagate. You will also have some electron-electron interaction. So this is called ionized impurity scattering. So if you start to dope, your system quite a lot, then you have interaction between the electrons themselves or the hole. Then you can have some sort of extrinsic defects, so defects, alloying, and all other sort of source of scattering. And so in this presentation, I will really focus more on the last part, so the drift mobility. So if we go back to what we saw yesterday, in this talk, what we care about is the current density. And one can show that this is linked, and it should have sort of make sense to you from yesterday, that this is linked to the Green's function. So it was presented that the Green's function is the propagator. You create a particle at a position, and then you annihilate it at a later position and time. But in this case, we are interested in the current at a specific time. So what is my current at this specific time and position? And so I'm interested in the change of sort of my particle, so the gradient, if you want, of my Green's function at a specific time. And so the Green's function is defined as this thermodynamical average of Heisenberg field operator that are themselves the time evolution of your Schrödinger field operator. And so in practice, if we want to compute the Green's function, one of the issues is that these exponential have these Hamiltonian and those don't commute. And so that's a bit of an issue. And so one way to go around this is to use the contour formalism in which you recast your solution, not in space, but also in complex time. So you have this contour in which you have some complex part. And so now instead of time, I have this z, which is this complex time. And then what we can do is we can do an expansion of our Green's function. And so we can expand our Hamiltonian into a non-interacting part, an interacting one, and a part due to the external field or external interaction. And so if these two are relatively small, what you can do is you can do a perturbative expansion, so a Taylor expansion of the Green's function in power of your interacting Hamiltonian or external Hamiltonian, and you get this sort of very long equation, in which you have the non-interacting Green's function given here, which is given in the product of those two field operator. If you express all your Hamiltonian in terms of field operator, you can then use Wick's theorem that basically allows you to rewrite all of this product of psi in terms of product of only two psi, so in terms of product of non-interacting Green's function. And that allows you to solve the resulting expansion with Feynman diagrams and to obtain the sort of famous Dyson equation. So this is the Dyson equation. And here I'm using a new notation, which is this 1 and 2. And so 1 and 2 denotes simply the space position 1 and the complex time 1, and the same for 2. And so this Dyson equation sort of connects the non-interacting one with or full one through what is called the self-energy that was also presented by Feliciano yesterday. And so then what we can do is we can use Langred rule. We can give an explicit form for a non-interacting Hamiltonian. And we can also evaluate our Dyson equation at equal time, because remember, what we care about is the current density at a given time. So we want to evaluate this at equal time. And so you have to do a bit of math there, but then you can obtain the so-called one of the Kardanov-Baum equation of motion. So this is the one for the lesser Green's function. But actually, you have 7 Kardanov-Baum equations for all of the possible G. So you have the lesser, the greater, the retarded, and so on. But this is the one we care about for transport. And so this equation gives you the change in time of your Green's function, and it's equal to those 4 terms. So you have the unperturbed time evolution of your lesser Green's function. You have this local time self-energy, because here you can see that I only have 1 time indices. And then you have those 4 terms here in blue, which describe all the internal dynamics. So this is all the correlation, the scattering, and so on. And you can see that here I have also this self-energy that appears. And so this is really the most general, sort of exact many-body equation of motion. And so what I'm going to try to do is to show you the steps, the approximation that we need to do in order to go to the Boltzmann transport equation that we will use this afternoon. So the first approximation that we can do is we can approximate the exchange correlation potential, and we can evaluate it at the non-interacting one. And this allows you to then simplify your equal time self-energy in terms of this external electric field like this. If you then consider that your the applied electric field is homogeneous in space, so this is not an approximation. Let's say in many experiments, you apply a very macroscopic electric field, so it sort of makes sense. And then in that case, you can express this in terms of the applied electric field and the position. And then this term reduces to a sort of simpler form in which you have the electric field, the position, and then your lesser Green's function. Now, what we can do is we can block project. So this is not an approximation, it's just we are changing our reference frame. But what we are doing here, we are doing an approximation which we are considering only the diagonal matrix element. And this should be a relatively good approximation if you don't have band mixing. And so what you're doing now is that you are injecting here these block wave function that you expand in plane wave, and you integrate over R. And so you're basically factoring out your position, degrees of freedom, for momentum 1. And then you obtain this equation where I have defined a sort of generalized occupation function that is defined as such. So you have your lesser or greater Green's function that is basically block projected. So this is simply a definition. And so you get that this is equal to your field and then the derivative of this generalized occupation function. And so if we do, basically, if we go back to our Kardanov-Baum equation, of course, through the definition of this f function, you directly get this term. This term we've done it together. You can show that this term is actually 0, and you're left with this big term there. And so you end up with this quantum Boltzmann transport equation in which you have the evolution of your generalized occupation function. This is the driving term that comes from the electric field that you're applying. And now you have on the right-hand side all the collision term that I mentioned about. And here I'm also introducing and defining something very similar. This is this gamma function, and this is the block projection of my self-energy. So it's the same thing as for the Green's function, but now I'm doing the same thing for the self-energy. And so there you get what we refer to as the AC, or the quantum Boltzmann transport equation, or the AC Boltzmann transport equation. AC because you still have a time dependence. So you can really describe a field that is changing in time, that is oscillating, for example. Okay, so now if we consider the DC limit, so the time, the case in which your field is time independent, then of course the first term is 0, and then you're left with those two terms. And because you are now time independent, you can have only difference of time or one time, and therefore you can do a Fourier transform, and you can Fourier transform your equation, and now you are in frequency domain. And here I'm introducing yet another notation, which is this f without the lesser and greater, and this is the integral, the frequency integral of my generalized occupation function. And this gives you actually the occupation function that you are familiar with. So in a code, you will have the occupation of each state, but this will be the occupation in the presence of an external electric field. Now, the main issue is, of course, the right-hand side term, because we don't really know how to compute this generalized self-energy. And so here we really need to make a lot of approximation. So if we only consider scattering by lattice vibration, if we neglect phonon-phonon interaction, if we assume that our electron-phonon matrix elements are frequency independent, if we consider the phonon-Green's function in the adiabatic approximation, and also if we approximate our generalized occupation function, so we do all of this, then one can show that this term reduces to a more manageable one, which is the one that you see on the right-hand side, and you can recognize the electron-phonon matrix element that you've worked with during the hands-on yesterday. And also, you have this 4 energy conserving term, where you see this occupation function that depend on the field. And so these 4 energy conserving term describe the fact that you can get in or out of the state Fnk by either emitting or absorbing one phonon. So you have 4 possibilities. And this is really what this equation tells you. And so this is the Boltzmann transport equation that we will use. You can see that it has this dependence on field. So once we have the Boltzmann transport equation, what can we do? Well, we can go back to what we want to compute. So we want to compute the current density, but we want to have the macroscopic average of that current density. And so I'm back to my original equation, but now we can do the block projection and all the steps that we have done. And so this lesser Green's function reduces, under all this approximation, to this occupation function that is field dependent. And also the gradient will give you the electric velocity, the velocity of your constant state. Okay, and then if we consider the linear response, so we are in the weak electric field regime, in that case, we can define the conductivity, and this is by definition defined as the change of your current density with respect to field evaluated at 0 field. And so for this, I'm also introducing this notation just to make it a bit more compact. But so what you're interested in is the velocity times the change of my occupation function due to an external electric field. Now, in practice, experimentalists, they prefer the mobility instead of the conductivity, because in an experiment, it's often difficult to know how many doping or carrier that you have. So what you do is that you divide by the carrier concentration, and the resulting quantity is called the carrier drift mobility, and that is independent on the carrier concentration. Therefore, it's a really intrinsic properties of your materials, and it describes how your electron or your hole can propagate, or how easy it can propagate in the material. So basically, what you need to compute is this object. So what you can do is you can see, so what you need is the derivative of your occupation function with respect to field. So what you do is simply you go back to your Boltzmann transport equation, you derive with respect to field on both sides. So this dies out, you're left with this term, and then this term you will have many derivatives with respect to field for all the f. But you can see that you also have f mk plus q, and so what this gives you is this self-consistent equation, because you can see that on the left-hand side, I have the term that I want in my equation, but this term also appears on the right-hand side, but at a different momentum. So this is k, which is the electron momentum, and q, which is the phonon momentum. And so to solve this, you have to solve it iteratively. And here I've also highlighted the tau, so the scattering rate here, which are directly connected with the electron-phonon matrix element, and was also touched upon yesterday by Fei Chano. Now, if you don't want to solve this equation self-consistently, what you can simply do is kill the second term. And in that case, you have a much simpler expression that we call the self-energy relaxation time approximation, in which now your term is simply the velocity, the change of occupation, and note that there is a 0. The 0 means that this is the occupation without an electric field. So this is simply the Fermi-Dirac occupation function. with respect to energy, and then you have your scattering rate or scattering lifetime. And so the reason we call it the self-energy relaxation time approximation is because your mobility is then directly proportional to this scattering rate. And actually, you can show that the scattering rate is exactly 1/2 times the imaginary part of the electron-phonon self-energy. So you have a direct connection between your mobility and the imaginary part of the electron-phonon self-energy. Okay, so now we would like to solve this in a computer, let's say in EPW. The main issue that we are facing is that we need to do an integral over momentum, actually a double integral, both over electron momentum, but here you can see that I also have integrals over the phonon momentum. So I have sort of 6-dimensional integral to be performing. And the main issue is that you have term like this one, where you derive the Fermi-Dirac with respect to energy, and that's a very peaked function. So this is what the function looks like. And this also makes sense because the transport always happens at the edge of your bands. So you basically thermally excite some electron, and so all the electron or the hole that will move, in this case the hole, they will all move really at the edge. So you want to really finely describe all your state very close to the band edge. So in this case, it's the gamma center band edge, but also this is diamond, so you also have in the conduction band, you have at this sort of position, you have to very finely describe your state. And this is really why we need an interpolation technique, because otherwise it's way too expensive. And so this was presented yesterday, but the idea of EPW is that you're computing your dynamical matrix and electron-phonon matrix element on a coarse grid. Then you have to subtract the long range, and I will spend a bit of time on that to get the short range part of this quantity, and then you can do an accurate interpolation to very, very dense grid at a low computational cost. So I want to spend a bit of time on this long-range expression because those are very important to get high quality when interpolation for your electron-phonon matrix element. So here I'm expressing the electron-phonon matrix element. This is in the mode basis, so I'm just factoring out the eigen displacement vector and the mass and so on, and I'm left with this electron-phonon matrix element in the Cartesian representation, and I can express that in the short-range part plus this long-range one, okay? But here I have made it very explicit that we are in a one-year framework. So this is the one-year rotation that you are doing. The U is the periodic part of your wave function. And if you do the one-year rotation, you're basically mixing your periodic part of the wave function with different state through this unitary rotation U. And so these U of W are the periodic part of your wave function in the one-year basis. Okay? And it will become clear why I make this very explicit. So this is this term, and the U are the rotation matrices from 1 year. And why do we want to do this? What is the main reason? If you look at the electron-phonon matrix element, the real part and the imaginary part, as a function of Q, you can see that they're completely random because you have a random phase. And so this is not great if you want to interpolate. You would like to have something smooth. Note that the absolute value is smooth, except at gamma, but the individual real imaginary part are not. Instead, if you do this rotation in the 1 year gauge, then you have something very smooth, again, except at gamma. And so this is much nicer for interpolation purposes. And so now we are left with the term that you can see here, which is the long-range perturb potential. And so for that, we need analytic expression, even if they are non-analytic when we go to gamma, but expression that we can subtract and add at arbitrary Q points and K points. And so if you do the expansion, you can do this multipolar expansion in terms of dipole, quadrupole, and so on. So you can see here I have Born effective charge, dipole, I have quadrupole, and I also have this additional term. What is quite important here is the F. So the F is a range separation function. So it splits basically your potential into a short range and a long range term. And in the case of bulk 3D, it's basically an exponential like this, and this is called the Ewald factor, in which you have a range separation length L, so this is in Bohr, and the way to compute the optimal L is to minimize your short range dynamical matrix. That's one of the possibilities. But so the reason I'm presenting it in this way is because you can then extend this to the 2D case, and it's a bit more complicated, but you can see that the structure is very similar. So you have sort of in-plane component and you have out-of-plane component. And what's quite remarkable is that even for the in-plane contribution, you have out-of-plane contribution. So you can see that here I have my quadrupole in the out-of-plane contribution that have an impact on the in-plane electrostatic. So it's really important to include those if you want to describe your system quite well. Now, the range separation function in 2D is different. It's an hyperbolic tangent instead of an exponential. But basically, the concepts are quite the same. And now I have two sort of dielectric function. You can see here also this optimal L parameter can be computed and has a value. And this is done automatically in EPW for you. Oops. So one thing that I want to mention that's relatively recent is the fact that because we are smooth, this is the reason why we are using a one-year gauge, then you can do a Taylor expansion of your one-yearized periodic part of the wave function. So here I'm doing a Taylor expansion in Q, so this is the first order. And if I plug this into my equation that you see here and here, what I end up with is basically product of course, this guy and the other one on the other side, but I also have the derivative. And so you will end up with a delta, but you will also have other term, two first order in Q, that look like a Berry connection. So it's quite surprising, but you actually get the Berry connection that comes out because of this Taylor expansion. And the reason those are important is because this Berry connection term A is at the same order as the quadrupolar contribution. So if you only include dipole, you don't need this term at that order. But if you go to second order, so if you want to go to quadrupolar order, this is at the same order and therefore should be included. The same goes for this term, but it has been shown numerically to be quite small. So here we're going to neglect it, and we're only going to compute the Berry connection, the quadrupole, and the dipole part. So are those important? So this is a 2D material, SNS2. And here I'm showing the deformation potential. So yesterday you've played with the G, how to show and compare the electron-Phonon matrix element. And the deformation potential is very similar quantity, but you factoring out the frequency, so you can really focus on the electron-Phonon matrix element. This is why we sometimes prefer the deformation potential, but also because you can sum over bands, so electronic bands, so you can sort of show more information in a single plot. So this is a mode-dependent quantity. So I'm showing the deformation potential at the k point equal gamma as a function of q for all the modes in this material. And I'm looking at the band that are at the conduction band, minimum. And so the dots that you see are direct DFPT calculation, what you have done yesterday. And the interpolation is the interpolation where the long range includes only dipole or dipole plus quadrupole. So you can see that, in particular, this LO mode is really badly described if you don't use quadrupole. So it's very important. Now, what about the Berry connection term? So this depends on material. In particular, strontium oxide is a bit particular because by symmetry, the quadrupole are zero. This is one of the few materials that have zero quadrupole. And so if I do everything, but remember the quadrupoles are zero, I get this interpolation, but in particular, you can see that you have some oscillation here on the TO mode. And if I add the Berry connection, I improve the quality of the interpolation. And there is another, a bit more subtle importance of the Berry connection is the fact that it restores gauge covariance in the long wavelength limit. So what it is if I put my one-year center in my primitive cell, I get this. So R is the primitive cell. I get one solution. But now, if I put it in the next cell, in principle, I should get the same solution. I just get like an exponential factor. That's of course correct. But I should get the same solution. This is the full one computed directly. And now, if I subtract the long range, I get this short range real part of the G, but I can do the same for the imaginary part, of course. And you can see that if we don't have the Berry connection, we are losing gauge covariance. And so you really need it if you want to recover the correct result. So, of course, because we do a Taylor expansion, we only recover it to the first level. So we only recover it in the small region and not everywhere, because there we would need to do an infinite Taylor expansion. But at least we get some gauge covariance back. So is it important? So I've shown that it can be important for the deformation potential. Is it important on integrated quantity like the mobility? So this is the mobility of MOS2 as a function of temperature. So you can see the reduction of mobility as I increase the temperature. This is the electron mobility, and this is the intrinsic Hall mobility. And on the right-hand side, I'm showing the Hall factor, and I will talk about it a little bit later. But what is important is that you can see that there is a big difference. If I only include dipole or dipole quadrupole, I'm reducing quite significantly the mobility by about 40%, and therefore it's quite important. Here I will not spend too much time, but I'm just mentioning this because this is implemented in EPW. What is very important for transport is also to compute accurately the electronic velocities. And we have two ways to do it in EPW. One is based on computing directly the commutator, but one can also do it in a 1-year framework following very similar IDs as in the 1-year-90 software. And so those are two options that you will have in EPW, and there are advantages and drawbacks, and I can talk more about them during the hands-on. So how does this work? So I've shown some results for 2D. So this is 3D. I'm showing 10 very simple semiconductor. And for each of them, I'm showing the electron and the hole mobility compared to experiments. So you can see that typically we are quite good. We overestimate experiment quite a bit, but this is expected. And so we can study sort of systematically many materials. But what is very powerful about a technique like this one is that you can start to really look at the microscopic information. So you are making no assumptions, so you're computing all the Phonon modes, so you have all the information. And so you can do spectral decomposition, and you can notice that some materials are the mobility is reduced mainly due to acoustic scattering. In other materials, it's dominated by optical scattering. So for each material, I'm showing in green the hole and in orange the electron. But so because I'm including everything, I don't need to choose sort of which scattering mechanism I'm including. So sometimes one can do calculation with only one type of scattering, but here we are really including all of them. So we can also describe sort of cases that are in between, like those where you have both important acoustic scattering and optical scattering. Now, if I compare to experiment, you can see that the results are quite good at the self-energy relaxation time approximation level, but you can see that in some cases we underestimate experiment. And this is something we really don't want to do because we are only including the scattering with the lattice, but in reality, in an experiment, what you have is that you have also scattering with defect impurities. Your sample is never pure. So you actually expect to overestimate, you would like to overestimate experiment because you don't include all the scattering mechanisms. And so this is really, the reason being really that the CERTA is an approximation, and we can do better, we can do the self-consistent full Boltzmann transport equation. And in that case, you can see that we now sort of overestimate a bit the experiment as we expected. But actually, what I haven't mentioned is that most of these experiments are not time of flight, which would correspond to drift, but they're actually whole mobility experiments. So in a whole experiment, what you do is that you apply an additional magnetic field orthogonal to your sample. And what is happening is that your current, so you have the electric field like this, the electron, the charge will come, and due to the Lorentz force, the electron will be deflected on one side of your sample, and this will generate the whole voltage from which you're going to extract the mobility. And most experiments are done like that. Now, the issue is that, of course, the magnetic field is an additional driving term, so it will increase sort of the velocity of your electron, so you need to take it into account through what is called the Hall factor. So what you do is that you go back to your Boltzmann transport equation. This is really the same one as the one I showed before, but now I have an additional term. This is the term that I'm showing here, and this is a term that is due to the magnetic field, so you can see that you have a finite magnetic field, and in EPW we can have finite magnetic field, and then we do finite difference. Of course, this is only valid in the limit in which the magnetic field is not too big, because if you go in very high magnetic field, you start having discretized level and things like that, that Landau level and so on, that we cannot describe with this level of theory. Okay, and so we can do that, and then we obtain the green square, in which this is really our most accurate sort of prediction or calculation, and you can see that we now quite strongly overestimate experiment, sometimes by a factor of 2, but it is somewhat expected to overestimate experiment. What I want to point out is that the Hall factor, and this is often used in literature to say that the Hall factor is unity, but as you can see, it's not the case. So it's really unpredictable. You have to compute it. In some cases, it increases with temperature. In some cases, it's sort of flat. In some cases, it decreases. Sometimes it's much bigger than 1, sometimes much lower than 1. So you really need to compute it. We think it's quite important. Now I want to briefly show some example of what one can do. So here we've looked at sort of standard sort of mobility, but what you can also start looking at is, for example, how your mobility change if you do strain engineering. So if you pull off your sample, what is happening? And so, for example, here we looked at that, and what was happening is that you had the band inversion, and so this was increasing the whole mobility quite a lot. So we were excited by this result that you could increase via strain engineering. And of course, this has been done by engineers since a very long time ago. But we can see that we really describe this quite well. So this was gallium arsenide. This works also for scandium nitride and many other materials. Maybe a sort of recent one that I would like to show is not yet published is basically I've been interacting with an experimentalist PhD student for whom his experiment was actually not working. There was some technical issue, and he actually learned how to compute the mobility himself. And he was able to, and he looked at basically the impact of uniaxial strain on silicon. But in his experiment, he could do like a very small sample in which he can, so it's called lab on chip, and he could really pull the sample very much more than typically what you can do. He could do like up to 1 or 2% strain. And so you can see that what's very remarkable is that in the strain direction, you can increase the electron mobility, and in the other one, you have sort of a minimum. And so this predicted minimum was 0.03. And then another sort of prediction is that this is flat, and this is known in the literature that the whole mobility doesn't change with that kind of strain, but nobody has gone much further than 0.2%. And if you actually go further, you can double the mobility, so this is quite important. And we were almost ready to submit the paper, and a few weeks ago, he actually managed to do the experiment. This is what he got. And so I was quite surprised that it matched quite well. So in particular, this minimum is quite close. And so this is his sort of setup. So he's now trying to do also the whole dope. This is n-doped. But what I want to also emphasize is that I think the codes are now in a state that they can be used by experimentalists and other people. So this sort of demonstrates the easiness at which people can use this software. So now what happened in the case in which you dope a lot the sample? So if you dope, you continue doping, you have an additional scattering mechanism that will occur, and this is called carrier impurity scattering. And so this is a work of Josh and Feliciano, in which they implemented an ab initio way under certain approximation to compute this scattering rate, and this is implemented in EPW and will be done this afternoon. So the approximation is that you assume that your point charge is embedded in a dielectric continuum. You use the first-born approximation. You consider that you are in the dilute limit, so you have sort of randomly distributed impurities, and then you can write that your scattering rate is equal to this object. What is important is that in the denominator, you can see that you have a non-integrable divergence, but you can regularize it because you can realize that actually what you're having a lot of doping. And so this extra amount of charge will screen your interaction. And so you can use a screening model, in this case, the Thomas Fermi models, but you can use other like RPA screening. And this sort of regularized your expression. And so they were able to do this very nice result. So this works very well for silicon. This needs to be investigated maybe a bit more systematically in other materials, but at least here it works extremely well. So you can see here the reduction of electron and hole mobility for silicon as a function of temperature for different doping concentration that are given here, and their comparison to experiments. So the agreement is quite good. And the same here, if you increasing your concentration of ionized impurity as a function of carrier density for room temperature, you can see the decrease is relatively well matched. But one of the nice things that you can obtain from this is you can assess the validity of Mathison rule. So Mathison rule is used for many different things, but it can also be used to add different scattering mechanisms and to add different contribution to the mobility. So you can do this inverse sum, in which you've computed here the Phonon limited mobility, that's the one I showed before, and you can compute the mobility only due to impurity, and then you can sum them. And you obtain, so this is for different materials, you obtain this dashed line, and you can compare that with the full solution, in which you're putting both the electron-phonon scattering rate, but also the impurity scattering rate directly in your iterative solution. So this should be more accurate. And you get the plane line that you see. And so you see that there is a difference, and note that this is a log scale. So you can have like up to a factor 2 differences because you're using Mathison rule. So Mathison rule is not always a very good approximation. So now let me briefly expand what I've shown to the case of metals. So of course, in metals, it's a bit different. You cannot compute anymore the mobility because independent on the carrier at the denominator. Instead, you can compute the conductivity or the resistivity, and this is usually what is given by experimentalists. And you can do exactly the same thing as before. You can solve the Boltzmann transport equation, but you can actually do a further approximation. And I'm showing this because this has been used in the past in the literature. And in particular, if you assume that your electron-Phonon matrix element is constant close to the Fermi level, this is typically, for metals, is typically a good approximation, but you might have metals in which it's not the case, so you need to be careful. And you're also making this approximation. In that case, you can obtain what is called the lowest order variational approximation, or LOVA. And this is also sometimes called the Zeeman formula because it was introduced by Zeeman. And the formula is given as such. And so the reason why sometimes we like this formula is because now you can express it in terms of the Eliashberg spectral function. You can notice the transport, so it's a slightly different version of the Eliashberg spectral function. This will be presented in detail by Roxana in the next talk. But basically, this Eliashberg spectral function is proportional to the Phonon frequency, and then the mode resolve transport coupling strength. And the point is that sometimes you have access experimentally to this quantity, and therefore you can predict the resistivity from this quantity only. So here I'm just showing how does that work. In one case, this is lead that you will also do in the tutorial. So of course, in lead, spin-orbit coupling is important. So you can see the difference in Eliashberg spectral function with and without spin-orbit coupling. And if you inject that into the Zeeman formula, then you get this resistivity as a function of temperature. And this is compared to the experiment. So you can see that the beginning is quite good, but then as we go to higher temperature, the agreement gets worse. Notice that, of course, lead is a very soft metal. So actually around 600, you are very close to the melting point. But we've also done the Boltzmann transport equation on lead and looked at many different contributions to try to fix this high temperature dependence. And in particular, we looked at also the effect of thermal expansion, because of course, when you go to this high temperature, thermal expansion is important. Okay, so this is actually most of the theory I wanted to present. So a bit fast, but it's fine. I still have some slides because I want to show some of the recent development in the literature and basically where where I think the field is going in terms of transport. Some of them are on work, but we also have many other. I just saw that there is an alert, but okay. Okay, so the first one is what is the effect of anharmonicity? So you can compute an harmonic effect because, of course, in some materials, either at very high temperature or in some very anharmonic material, you can get soft mode. So in case of soft mode, it's not really well defined, within this theory, what we should do, in particular, to compute the electron-Phonon matrix element. And so there are many software that can allow you to compute the contribution from anharmonicity. So you have TDEP, SHA, different flavor, a la mode, and also the ZG software that will be presented by Marios Zacharias on Friday. And so you can see here for strontium titanate, the effect of anharmonicity. So if you don't include anharmonicity at room temperature, then you get soft mode, which is expected because at that temperature, you get those soft mode. But if you use TDEP, then you can basically recover the experimental results. So this is quite good. And so then you can use this effective harmonic potential to compute the reduction of mobility. Another important development is the going beyond the adiabatic approximation and also including dynamical effect in the phonons. So of course, your phonons that we compute via DFPT are well-defined quasi-particle. They are basically adiabatic static, but in reality, what you really have is a spectral function. So you have a phonon spectral function. So this is here I'm showing the phonon spectral function on tantalum disulfide, and what you see is that there is two effects. One is due to non-adiabaticity, and you get sort of cone anomalies, all these peaks, but you also have dynamical effects that are really contained in the spectral function through the satellite and all these things. So you can see here those dynamical effects if I zoom in this region. And of course, all of these will have some effect on your phonon and will have some effect on transport. So as far as I know, this full dynamically dependent phonon spectral function was never really used in a transport calculation, but I think this will be only a matter of time, and this is really also where the field is going, because in some cases, this is very important. Now, all I've shown was the Boltzmann transport equation for electrons. But actually, you have a very similar Boltzmann transport equation, but for phonons. And this describes the transport of heat. This is heat transport. And because those two equations are very similar, what you can do is actually couple them. And so the Helf-Bolt software by Nakib Protik basically describes the linked Boltzmann transport equation. So because, of course, your electron, the electron population will change, and then the phonon population will change, and those will sort of interact on each other, and you can solve this self-consistently. And so what it gives you access to is things like phonon drag and thermopower, and this is what you see here. Another development is the electron-2 phonon scattering. So instead of having electron-phonon, you have an electron and then two phonons. This was done for gallium arsenide. As far as I know, it's only been done for gallium arsenide. And in that case, it was shown to be quite important to recover the experimental result. Otherwise, you overestimate the mobility quite strongly. One needs to see now if this gets applied to other material. If it's always important, I don't know, but it could be. So it's quite interesting. Another limit that I have not talked about is the high field limit. So in practice, of course, you sometimes apply high electric field. You don't apply just small electric field. And then that's non-linear. So then you cannot use this linear regime, and therefore you cannot directly compute the conductivity like I showed it. And so you have deviation from the linear occupation factor, and you can see that this deviation can be quite big, close to 0 here. And this is a work by Choi. Another thing that I have not really touched about, but I've mentioned, is that in realistic material, of course, you have defects. And so once we want to compare to experiment, we would like to compare with defect. And so this is a work on neutral defect, but in primitive cell only. So that's quite interesting. And this could also be in the future applied to reducing the mobility. Now, another one is the so-called relaxon. So you have relaxon for phonon, but also for electron. And so the idea of relaxon is that you have your scattering matrix that you diagonalize, and then the relaxon are the eigenstate of that. And this gives you some information about what sort of states are important, what scattering dominates. And in this work, what they've also looked at, they've used the relaxon picture, but they've actually computed the nonlinear hole conductivity ratio. So you divide this by the standard linear conductivity. And this is actually what is called the current responsivity. And they've computed it in germanium telluride. And so this was probably the first time that this was done fully ab initio. And then the Phoebe code can allow you to do this relaxon both for electron and for phonon. And so this, in principle, is a different picture, but should give you the same result as the full iterative Boltzmann solution. And here they've computed it for both the electron mobility, but they can also do the phonon thermal transport. And so from that, you can, of course, imagine that you can compute thermoelectric properties, Seebeck coefficient, and all these things. Another thing that's quite important is electron-electron self-energy or electron-electron correlation. So now, today and in most of this workshop, we will be focused, at least at the beginning, through electron-phonon, but then we will have GW electors, so we will also have a flavor of electron-electron self-energy. And so once you have those two self-energy or spectral function, what you can do is you can use the Kubo transport formula. And I have not explained it, but in the review that I showed at the beginning, there is an explanation of that. So if from the many-body, a quantum equation of motion, if from the beginning you linearized, then you obtain what is called the Kubo transport formula, in which you have a direct connection with spectral function after some approximation. And so what you can then do is sum your electron-phonon spectral function and your electron-electron spectral function, and then solve the Kubo formula to get transport result. And so this was done here in strontium rutanate. And you can see that, this is considered a strongly correlated material. And indeed, so they've used DMFT to compute the electron-electron spectral function. And you can see that the electron-electron spectral function dominates the resistivity, but this is not always the case, and there are other materials in which the electron-phonon does dominate. And so I want to finish with sort of a very recent trends that you are all aware of, is the fact that now we have a lot of machine learning, and actually there are some quite interesting recent papers in which they do machine learning on density functional perturbation theory. And so they use this deep H and so on neural network to compute these things. So this looks very promising. You can also do machine learning or just a lot of material. So if you compute many Boltzmann transport equation, you can use this data to also make prediction, or you can directly learn the perturb potential and train on the perturb potential, which is more what they've done here. And there have also been new recent papers on compression methods, compression algorithm in order to speed up the calculation. So basically, it's an open question if we will all be out of job or if we all have to switch to machine learning. So I leave that up to you. And I thank you for your attention. But maybe let me just conclude, because I guess I have still a bit of time. Yes. So basically, yeah, the overall theme is that maybe the main message that I wanted to carry was the fact that you can really start from the most general quantum equation of motion, and you can do a well-defined step of approximation to obtain the Boltzmann transport equation. And the reason we really worked on that is because now one can try to remove some of this approximation and go up the ladder and become more and more accurate. And I would argue that for that reason, the Boltzmann transport equation is not really semi-empirical, because it can rigorously be derived from a many-body framework. I've shown that long-range electrostatic is very important, especially in 2D materials. So you need to account for dipole, quadrupole, and also this Berry connection term if you want to accurately describe your electron-phonon matrix element, but also if you want to accurately describe your phonon. So the dynamical matrix, you need to do the same thing. You can also show that if you don't do that, then you will have some issue with the CASP and so on of the phonon frequency close to the zone center. I've shown that the whole factor is temperature dependent and can deviate from unity. So if you want to compare two experiments, it is good to actually compute that ab initio. In general, Boltzmann transport equation mobility overestimate experiment, but this is actually a good thing, because in reality, you also have many other scattering mechanisms. So when you include those, you expect to reduce the mobility. So you typically want to overestimate a little bit. And also I've shown that carrier impurity scattering is very important if you want to look at highly doped material, and this will also be shown and discussed this afternoon. Thank you.
Thank you, Samuel, for the very nice talk. It's a lecture. So now we have plenty of time for questions. Or we first take questions.
So if you have kind of a consistent overestimation of connectivity and mobility in the computation, what's kind of the best practice for converting a computed value into something that you could expect in an experiment if you're looking at new material and effective fits?
Okay, so you can see indeed that you have sort of an overestimation. Maybe I shouldn't say that, but basically there are a few materials that are quite strongly overestimated, but actually those experiments are from the 70s, and I couldn't find any new experiment. And it seems like, experimentalists, they don't want to do like boring materials. But so I do think that a few of them might get closer if you do more recent experiments. And indeed, the more well-studied material like silicon and diamond, you overestimate much less, right? So that's the first thing maybe I can mention, is that if you compare to recent experiments done on really pristine, intrinsically doped sample and so on, you can expect a closer agreement, but you do overestimate. And so I haven't shown it, but actually in this paper, what we do, you can see that there is still two space here, which I'm not showing here. I don't know if I have it in supplemental, but basically let me see if I have it. I'm really not sure, because that would actually answer your question. No, sorry, I don't have it. So you'll have to go and look in the paper. But basically what we did is we tried to correct indeed. So we tried to correct our equation. So one of the issue of DFT is that you may know that the dielectric constant is typically overestimated because you underestimate the band gap. So you will typically overestimate by 20% or so your dielectric function. And you know that your sort of, this will sort of, underscreen somehow your matrix element, and then you will overestimate. So what you can do is simply rescreen your matrix element by simply multiplying and dividing by the experimental dielectric function, if you know it, and the one that you compute. This will rescale, and you will get a bit closer to experiment. So that was one thing. And the other thing that, to me, is still surprising is that effective mass in DFT are sometimes not very well described. And this is something that people don't look so much at, in my opinion. So we still have some issue in some material in some direction. And so we also looked at correcting the effective mass by using the experimental one. And that typically brings you also a bit closer to experiment. So there are ways to, if you have some experimental information, you can try to tune back a bit. And so that if you have partial information on your materials, you don't have, let's say, the mobility, but you have this quantity, then you can expect to improve a little bit your estimation.
Other questions? Other questions from people? If not, John, what about Andre?
Yeah, so the first one, I guess, is related to this one from the audience. The person is asking about what would be the effect of choosing different exchange correlation functions in the mobilities or in the resistivities program.
That I think I have an additional slide. Let me see. Yeah, so in fact, in that paper, we precisely looked at all of the effect we could think of. So the baseline is the most accurate calculation that we have using spin-orbit coupling, quadrupole, everything you want. And then these are, so for the 20 materials, both the hole and the electron, so this is the relative effect, so the deviation on the room temperature mobility for all these materials. If you have only dipole, if you have no spin-orbit coupling, if you do the self-energy relaxation time, if you use the lattice, if you use the experimental lattice parameter, you can see that there is a small difference, but maybe not so much. And if you change exchange correlation function. Admittedly, I only tested 2, so I did LDA and PB. But you see the difference between LDA and PB is really not so much. And this is the same functional, but using different pseudo-potential from different library. And again, I mean, here, I don't know, I mean, you get at most, I don't know, 15, 20% relative difference. One thing that maybe is interesting is the spin-orbit coupling. So actually, the spin-orbit coupling works always very well for the electron because typically the conduction band is well described. However, for the hole, you typically, due to spin-orbit coupling, you get a splitting of the valence bands, and that typically impacts the mobility a lot. And so you can see that all the deviation and the underestimation that you see here, if you don't include spin-orbit coupling, they are due. I mean, they're basically impacting the hole. So if you want to study the electron, you probably don't need spin-orbit coupling, except if it's a specific material. But instead, if you want to look at hole mobility, you should really include spin-orbit coupling, because you can see that I have here up to, I don't know, 70% differences. So maybe that's one message, is that for the hole mobility, it's very important, because even some small splitting in silicon, you have 47 millieV splitting, when you include spin-orbit coupling, and that 47 millieV splitting has a big impact because all the transport happens in a small window close to the conduction, the valence band edge. So maybe a 200 millieV window. So 47 millieV in that window is important.
Okay, and the second question is more on the theory. So you laid out several approximations. In particular, one of the first one was this diagonal block state projection. So could you comment a bit on the range of validity of this type of materials?
That's a good question. Yeah, so this is what I wrote here. The answer is I don't know. We haven't sort of that much investigated so much. But the hope is that indeed, if you don't have too strong band mixing, that you'd hope this would be a good approximation. Maybe in very small band gap materials, you might have some influence, because then the band might talk to each other through the different states. So that might not be so good. And in fact, Dr. GMO Lim had the paper, but that was on the self-energy and the 0-point renormalization, in which he considered this off-diagonal term. And in a very small bandgap material, it was important. But let's say for all the semiconductor that I showed, it shouldn't be important, I think. Yeah. But okay, I don't know is the answer.
Okay.